So we were trying to finish up 9.1, and we were on the third example to determine whether a sequence that's given is monotonic or not. So this is C sub n. Those terms are found using this formula. C sub n equals n squared over 2 to the nth minus 1. So let's start finding terms. If I substitute in 1, I'll get 1 squared over 2 minus 1, so that's 1. If I substitute in 2 for n, that'll be 4 over 4 minus 1, so 4/3. Put in 3, that's going to be 9. 2 cubed is 8 minus 1 is 7. 4, it's going to be 16. 2 to the 4th is 16 minus 1 is 15. Okay, so what I want to do is I want to see if these are actually appearing to be always increasing or always decreasing, or stays the same. So let me get my calculator to compare these numbers. I think it'll be easier with a calculator. So in decimal form, this is 1, 1.3 repeating. 9 divided by 7 is 1.286. Oh, look what happened. I'm not going to go any further. It increased from 1 to 4/3 and then decreased to go to 9/7. So there's at least one instance where it's going up, it's increasing, and another instance where it's decreasing. So I can't say it's monotonic. This one is not monotonic. And again, if you just show me, kind of prove to me there that you have increasing and decreasing behavior in the same sequence, like I just did, you can claim that it's not monotonic, and it's not that hard to prove. Okay, so the next idea is about the definition of bounded sequences. And if you have a sequence, we'll be able to call that sequence bounded above when there's some real number m such that a sub n is less than or equal to m for all n. And that is called an upper bound of the sequence. So let's look at the first one we did, the a sub n, which I wish I still had that available to look at. So I'm going to have to sort of make sure I create this correctly. That one was 2, 4, 2, 4, 2, 4, I believe. I think that's what it was. And is there a number m? Okay, I'll make up a number. Let's say, could m be 10? Is there a number m such that every term of the sequence is less than or equal to m? Well, yeah, 2 and 4 are the only terms that we're getting here, so they're all less than that for every n. So the first term, second term, third term, fourth term, etc., etc., etc. For every single term of that sequence, we're never getting a number that's bigger than 10. So m is an upper bound. Well, would 10 be an upper bound? Yes. How about 9? Would 9 be an upper bound? Yes. Would 1,000 be an upper bound? Yes. There are lots of upper bounds to this sequence. Sometimes, and that isn't in this particular definition, but sometimes we're interested in finding out, well, what is the least upper bound? What's the smallest number that we could pick for m such that every term in this sequence is less than or equal to that. The least upper bound for this is when m is 4. That's the smallest upper bound that we get. It's when m equals 4. Okay. Second, a sequence is bounded below when there's a number n such that n is less than or equal to all of the terms of the sequence for all n. That's called the lower bound. So looking at the same sequence, is negative 12 a lower bound? Is there any number that's smaller than negative 12 in that sequence? No. So n equals negative 12 is a lower bound. Is n equal to negative 6 a lower bound? Yes. Is n equals 0 a lower bound? Yes. These are all lower bounds that I'm listing. Sometimes we're interested in the greatest lower bound. What's the largest number that we can claim is less than or equal to all of the terms of our sequence? So in this particular case, the greatest lower bound is an n value of 2. If a sequence is bounded above and bounded below, then we can simply say it's bounded. So this particular sequence that we've been dealing with is bounded because it's bounded above and bounded below. So we can just simply say bounded. So if they say a sequence is bounded, that implies that it's bounded above and below for sure. Okay. Let's see. The next page. An important property of the real numbers is that they are complete. Informally, this means that there are no holes or gaps in the real number line. To contrast that, rational numbers don't have the completeness property. You might think about it this way. Real numbers include all rational and irrational numbers. So those irrational numbers are filling in holes between rational numbers because the combination of those two sets makes all reals. And so they're definitely not a completeness property when we're talking about the set of rational numbers. The completeness axiom for real numbers can be used to conclude that if a sequence has an upper bound, then it must have a least upper bound. And we actually already found that before. And so we can conclude that there has to be a least upper bound if there's an upper bound at all. And you can also say the same thing about the greatest lower bound. Same thing is true. So let's look at this sequence, a different a sub n, where this a sub n is defined by the formula n over n plus 1. And so if we find a few terms here, putting in 1, we'll get 1/2. Putting in 2, we'll get 2/3. Putting in 3, we'll get 3/4. Putting in 4, we get 4/5. Etc. Then the general term or nth term is n over n plus 1, comma, dot, dot, dot. So that's the full sequence using all positive integer values of n. So, is there an upper bound for this? Well, if you look at the sequence of values that we're producing, eventually we're going to get to, I'm just going to write some big ones, 99 over 100. And eventually we'll get to 999 over 1,000. And so, will these ever have a numerator that's equal to its denominator? No. Will the numerator ever exceed the denominator? It's not equal to it ever. Will it ever be bigger than the denominator? The answer again is no. So these values are approaching 1, and so 1 is greater than all terms in this sequence. I can't find something that it's or equal to, but I can certainly say in this case that the least upper bound for this sequence is 1, because the answers are getting closer and closer and closer to 1, never reaching it, and certainly not exceeding it. So that is the least upper bound that we can get. All right, so that leads us to Theorem 9.5. And this is why we needed that terminology about monotonic that we talked about earlier. If a sequence is both bounded, that means it's bounded above and bounded below, and it's monotonic, then it will converge, for sure. Okay? So, let's look at a few examples of that. A. The sequence A sub n that we're going to consider for this one is formulated by using the formula 1 over n for all terms of the sequence when we use all the domain members, all positive integers. So let's look at that numerically. 1 over 1 is 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, etc. Some of you have a pretty good numerical sense and have an idea of what's going on here. What I would like to do is also involve some more of you with this in a graphical way. So I want to graph this sequence. So let me set up my plane where I'm going to graph this sequence. Well, we don't need to label those numbers along the bottom. That was silly of me. I could have just labeled the first one with 1. Oh well, that's all right. Not going to hurt anything. Okay, so when n is 1, we got 1, 2, 1/2, 3, a third, 4, a fourth, 1/5, 1/6, etc. So in looking at this one, does it seem to be bounded above? I believe it does. It is bounded above. The very largest value we get is 1, and every other one does not exceed that. So all terms of this sequence are less than or equal to 1. Now, is there a lower bound? Can that ever be 0? Is 1 divided by something ever going to actually equal 0? No. Will it ever go lower than 0? No. 1 divided by a positive number is not negative. So it is bounded below by 0. As you can see in the graph, the highest value that we get is the highest point, and the lowest is what this is approaching. These are getting closer and closer to 0 as n increases to infinity. So all terms of the sequence are between 0 and 1, including 1. So therefore, this is bounded. Now, if you look at those, maybe you have a sense numerically of that, and I won't have to prove that it's monotonic. Perhaps in every case. I think this one I'll let slide. As the denominator grows and the numerator stays always 1, every subsequent fraction is smaller than the one before it. And so, yes, this is a monotonic function. I think maybe we should prove that this time. And I want to teach you another way. So what I suspect is going on here is that for any term, I think it's greater than or equal to the subsequent term. And that's what I'm going to
Mr. Ford, you there?
All right. So I said we wanted to prove that that's true. So actually this is in question. Is that really what's going on? We kind of perceive that it is, but we don't know. So I'm going to write down what our A sub n is in terms of a formula. And then A sub n plus 1 means I would substitute n for every n with n plus 1. So that would be 1 over n plus 1. And I want you to think along with me for a second about that. Numerically speaking, the denominator in the right-hand fraction is bigger. And when you divide by a bigger number, your answer is smaller. So the n plus 1 fraction with a bigger denominator gives us a smaller answer. And indeed, that says that that is true. And from that, we could conclude that for any two adjacent terms, that the one that's later, a sub n plus 1, will be smaller than the one that's before a sub n. And so this is a strictly decreasing function. So that means it's monotonic. So once we've established that it's monotonic and it's bounded, those two together mean that we can draw our final conclusion and say, by theorem 9.5,
Mr. Ford, you there?
sorry, you probably heard someone asking me something, or at least I think you may have heard it. So I had forgotten to put on my headphones so that you couldn't hear if someone came on and asked me a question. So, oh well, yeah, I'm sure you're fine with that. So by theorem 9.5, because we established that it's bounded and monotonic, we can therefore conclude that this sequence called A sub n converges. Okay, so that's that result. Okay, let's look at another example. Let's look at B sub n. Okay, B sub n is defined as n squared over n plus 1 So if we were to write a few terms of that, let's see, 1 would give me 1/2, 2 would give me 4/3, 3 would give me 9/4, 4 would give me 16/5, etc. So if we were to look at the graph of that sequence, let's see, let's make 1 about right there, 2 is up there, and on the n-axis that's 1. Okay, so 1 gave me an answer of 1/2, 2 gave me an answer of 4/3, which is 1 1/3. 3 gave me an answer of 9/4, which is, oops, I didn't give myself enough room, did I? Rats. I need to change my scale on the y-axis. I did not think that through ahead of time very well. Oh no, the order in which I did that stinks. Oh well. Sorry about that. I should probably do the n scale first, because that's always going to be 1, 2, 3, 4, 5, 6, whatever. So let me make one here about that big. I think this is going to be better. My apologies. Something a person should think through. All right, anyway, 1 is 1/2, 2 is 1 1/3, 3 is 2 1/4, 4 is 3 1/5. And if you look at the projection of those values and think about it, the numerator is getting big a lot faster than the numerator, than the denominator is, because squaring n makes n, that result, bigger than just n would be. And so the numerator is growing faster than the denominator, and so those fractions are getting bigger and bigger and bigger values. So, is this bounded below? Well, yeah, the smallest answer we got was 1/2. So b sub n is definitely greater than or equal to 1/2. Is it bounded above? Well, as we just indicated, these are just going to get bigger and bigger and bigger without bound. So this is only bounded below. So we're not going to be able to use theorem 9.5 on this one. That doesn't mean it can't converge. That just means we can't use that theorem to show that it converges if it really does. So we're not going to be able to use that theorem. And is it monotonic? Yes, I think we can clearly say from our numerical evidence that it appears that they're getting bigger and bigger always. So we're not going to have any decreasing. Again, and let me do one more example like this to show that it's what I perceive as that it's increasing. I could prove that if need be, by letting f of x be x squared over x plus 1, which agrees with our sequence at every positive integer n. And to see that something's increasing or decreasing, we use the first derivative test. So there's a fraction, so low d high minus high d low all over the square of low. And I'm going to do this one a little bit more fully than I did, I think, one earlier where I used this same rationale. I'm going to do this with a little bit more completeness. So that's 2x squared plus 2x, I distributed that 2x, minus x squared divided by x plus 1 squared. Okay, that simplifies to be x squared plus 2x over x plus 1 squared. And when I'm trying to find increasing, decreasing, one of the things we're going to do is find our critical numbers. This is a calculus 1 idea. So what we're going to do is set this equal to 0 and find out when it fails to exist. Those are where the critical numbers can occur. So having it in factored form is a really good idea because it makes solving these two possibilities way easier. So you can have a critical number for a function. Anytime the first derivative equals 0, oops, didn't mean to write equals there. Pardon me. Or the first derivative doesn't exist. So the only way a fraction can equal 0 is if the numerator is 0 and the denominator is not. So that would be when x times x plus 2 is equal to 0, which occurs at 0 and negative 2. Or a fraction will fail to exist if the denominator is 0. If you try to divide by 0, you won't get an answer. So if the denominator equals 0, it will fail to exist. And that gives us negative 1. Now, I don't know if you learned this in Calculus 1 or not, or even in pre-calculus, but this tool I'm about to maybe reintroduce you to, or introduce you to for the first time, is called the number line analysis. This is a great tool, and I think you should learn how to use it. If you think about all real numbers for x, the real number line that I've just drawn there represents all the x values possible. And on that number line, I'm going to graph all of the critical numbers. The least one is negative 2, then comes negative 1, and then is 0. Those are all of the critical numbers. Now, my notation to distinguish between the two types of critical numbers I got, anything I got by setting the first derivative equal to 0, because it's equal to 0 there, I'm going to put a dot on that number. Anything I get from does not exist, I'm going to put an open circle around that to help me remember that when x is negative 1, the first derivative actually does not exist. And that can happen for a variety of reasons, but those are places where I'd have to be a little bit careful. Now, this is what we call the first derivative number line test, number line analysis, excuse me. And so I'm labeling it as f prime. And what these three numbers do is they split the real number line into 4 different sections, 4 chunks. There's a set of numbers less than negative 2, the set of numbers between negative 2 and negative 1, the set of numbers between negative 1 and 0, and the numbers greater than 0. And the only way you could have a sign change is to go through, for a continuous function, is to pass through 0 or have a discontinuity happen, or some other reason that's either first derivative equals 0 or doesn't exist. So that's the only way you can have a sign change. So if I pick a number to the left of negative 2, any number I pick, if its answer is positive, then all numbers in that region will also be positive. If that number is negative, all numbers in that region will be negative. So looking at my first derivative, I'm looking at this right here, I'm going to just imagine that I'm putting in negative 10. And you can do this all in your head. I don't really care if you write this stuff down normally. But if I think about negative 10 put in there, just as an example, that's going to be a negative number. Negative 10 plus 2 is still a negative number. And whatever x plus 1 is, when you square it, it will be 0 or bigger. And since we're not going to let it be 0, it'll always be positive. So when x is negative 10, what will negative times negative divided by positive give me? The answer is it'll be a positive number. No matter what number I picked to the left of negative 2, that answer would have been positive. Okay, let's do another one. Between negative 2 and negative 1, I'm going to go up here, give myself a little bit more room. How about negative 1.5? So looking at that same first derivative that I have the arrow pointing to, negative 1.5 is negative. Negative 1.5 plus 2 is positive. And we already determined that the denominator is always positive. Negative times positive divided by positive is negative. So all answers between x equals negative 2 and x equals negative 1 will be a negative first derivative. Okay, between negative 1 and 0, let's try 1/2. 1/2 is positive. 1/2 plus 2 is positive. And the denominator is always positive. Positive times positive divided by positive is definitely positive. Oh, I meant negative 1/2. Hold on. Let me back up. I think I may have messed up. In fact, I know I did. Well, actually, I'm going to leave that particular answer, but I put it in the wrong spot. And I usually like to do these in order. We just picked a number 1/2 that's over to the right of 0, and we just determined that it's positive. I meant to do negative 1/2 and wrote positive 1/2, so I apologize. So between negative 1 and 0, let's use negative 1/2. So negative number, negative 1/2 plus 2 is positive, divided by always positive, will give us a negative result. Then below that number line, where we've indicated what sign the first derivative has, I'm going to label the bottom of that, but with f of x, and talk about what kind of behavior does a first derivative value that's positive indicate about the function's behavior. And so when the first derivative is positive, the function is increasing. When the first derivative is negative, the function is decreasing. Okay, so that's number line analysis, and for the first derivative to find out whether the function is increasing or decreasing, and on what intervals we could say that happens. Well, in the calculus 1 setting, we would maybe be graphing this, and we'd know now that the graph increases to negative 2, has a horizontal asymptote, and then decreases to negative 1. And this actually, the graph of this has a vertical asymptote at x equals negative 1, and then comes down, decreases from that asymptote on the right side of it, down to 0, horizontal asymptote, and then increases and it goes up. So we could find all that out about the graph from in a calculus 1 perspective, and that would be wonderful. But let's apply this now to what we're doing here. I know I got off track there for a little bit, but I think this was worth it because I think you should know how to find the intervals where a function increases or decreases. Now, keep in mind that n here is positive integers only. N is always greater than or equal to 1. So since we're letting x represent n, at least for this first derivative stuff that we did, if we only confine ourselves to looking at x greater than or equal to 0, well actually x greater than 0, let's just say that. X is 0, we just found out that that means f is increasing. So certainly the related sequence, when n is greater than or equal to 1, that's certainly numbers bigger than 0. That means that our sequence terms will always increase. So therefore, that's I and C. I don't know if you can read that. It's always increasing. So therefore, we could say B sub n is monotonic. So this particular one is monotonic, and it's increasing, and it's bounded below. And as it turns out, it diverges. Because it's not, if you look at the graph again, it doesn't head towards any particular value. So using everything that we just found, we can say, therefore, that the sequence B sub n diverges. Okay. Oh, by the way, the other way, there's another way we could have found out that that diverges. I'm just trying to see if we can apply the theorem 9.5 is kind of my focus here. But if we had taken the limit as n approaches infinity of our nth term, that goes to infinity over infinity. So I'm going to have to explore what happens if I have a function f of x that agrees with that for every positive integer n, and take the limit of that as x goes to infinity. The fact that that gives me infinity over infinity means that I could use L'Hopital's rule. This is just an alternate method for showing that this one diverges. And so the derivative of x squared is 2x. The derivative of x plus 1 is 1. And as x goes to infinity, infinity divided by 1 heads toward infinity. And that also is a reason that we could say that this diverges. And that's probably the most elegant way to show that it diverges. If that limit is infinite or negative infinity, you can say it diverges pretty quickly. And that's going to be fast and easy to do, I think, when it diverges. That's kind of nice. Okay, so now C sub n is negative 1 to the nth. So if I put in 1, I'll get negative 1. Put in 2, I'll get 1. Put in 3, I'll get negative 1. 1, negative 1, etc. So if we looked at the graph of this one, oops, give myself a little bit more this way. Okay, so graphing this one, then this one I got negative 1, 2 is 1, then negative 1, then 1, negative 1, then 1, etc. And these values oscillate between two values. And oscillation does not, by the way, imply that they have to be opposites. These values oscillate between negative 1 and 1. So it oscillates between these two values. So we're only getting two answers. It's kind of like that other one, 2, 4, 2, 4, 2, 4, 2, 4. That one also oscillates. But this one oscillates. Is it monotonic? No. It goes up, then goes down, then goes up, then goes down. So up, down, and then of course that means it's not monotonic. Okay, is it bounded? Yeah, actually it is. It is bounded. Oops, I forgot to say C sub n is, the least upper bound is 1. The greatest lower bound is -1. So it is bounded, because it's bounded above and bounded below. It's not monotonic, and it's not headed toward any specific value. And that's kind of the key, that it's not headed toward a certain value. So it does not converge. Therefore, C sub n does not converge, or we'll say it diverges. You can actually state it the other way if you want. Does not converge. It's also true. And one thing we were doing earlier, I'm not sure I did it every time. Yes, those inequalities I wrote beneath the graphs like a 0 less than a sub n less than or equal to 1, and b sub n is greater than or equal to a half. Whoops, sorry. A little slip there. There we go. So let's go back down to this graph. And oops, I didn't leave myself a lot of room there. So C sub n is bounded below by -1, bounded above by 1. Now that does not imply that it takes on every real value, because remember, these are sequences. We're just graphing dot, 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 dot. It's not connected. So although C sub n is truly less than or equal to 1 and greater than or equal to -1, it only takes on those two values. But this is still a true inequality for C sub n. So that's another way to indicate that it's bounded. So that would lead us to that statement. Okay, so that ends the section 9.1. Have a great time. I will see you in class.